told you wear the red bow tie. Just wing it. Just wing it.
All right. Hi, everyone. Welcome. Thanks for coming. As some of you may have noticed, I'm a little less talkative this morning. That's because I got quite a gnarly cold on Sunday and lost my voice for most of yesterday. So if I have to pause throughout the talk, apologies for that. All right. So for the past about year and a half, I've been working on the development of an optical plasma diagnostic for plasma weight field acceleration. Kind of break that down and go nice and slow through that throughout the talk. Before I get too far into it, just some quick acknowledgements. Thank you to the CU Warg team. It's been so much fun being a part of this research group for the past about 2.5 years. Thank you to all of you, everyone who came. I wouldn't be here without all of you, so thanks for coming. And yeah, thank you to the committee, of course, for being here and doing all this. Okay, a quick roadmap for the defense. We'll talk about the motivation, kind of why is this important, what is plasma weight field acceleration, and why is this diagnostic important for it. We'll talk about the physics background, how and why does this diagnostic work. We'll talk about the experimental setup, what does it look like, how did we construct it. Then we'll talk about some initial data that we've taken with the diagnostic to look at the sensitivity of the diagnostic, and then some future work to improve the sensitivity of the diagnostic. All right, so we're going to start nice and simple. If I want to accelerate a particle, such as an electron, to accelerate an electron, probably the easiest thing to do is take advantage of the electric force, the electromagnetic force. And so I can put like a positive plate on this side, and since opposite charges attract, the electron will be accelerated to the right. I can also put a negative charge back here, and because like charges repel, the electron will be accelerated to the right. Now, most conventional accelerators work based on this method. So this is an electromagnetic waveguide of a conventional accelerator. These plates that you see in the middle here are very similar to the plates that I just showed on the last slide. And so those plates will flicker back and forth between positive and negative charge in such a way that an electron constantly sees a positive plate in front and a negative plate behind. And so that's done using radio frequency waves. Radio frequency waves are sent down this tube, and they cause these kind of fields to oscillate between those plates. So if an electron enters from the left here, the electron will constantly see the same field and be accelerated forwards. Now, there's a big limit here, though. If you send too high intensity radio frequency waves down this tube, any imperfections in this electromagnetic waveguide will cause those radio frequency waves to focus in on themselves and form hot spots. And those hot spots are actually hot enough, or can be hot enough, to ionize the metal and form these craters. And the more craters that you get, the more imperfections there are, the more self-focusing you can get. And you basically start to tear apart your accelerator from the inside out. And so there's a limit to the radio frequency waves we can put into this and how quickly we can accelerate those electrons. One way to get past this is to use something which is already broken down. And that thing is called a plasma. What is a plasma? So gas is basically just neutral charge, right? Usually dominated by ballistic motion, so collisions between particles. A plasma, however, is a bunch of charged particles. And so plasmas are actually dominated by electromagnetic forces. And we can take advantage of this to accelerate our electrons. Some examples of plasma in the real world: stars are made of plasma, lightning is made of plasma. And the acceleration technique we use in plasma is called plasma weight field acceleration, or in short, PWFA. So we'll go through that kind of one piece at a time, because plasma weight field acceleration is kind of a lot of strange words squished together. So let's start with the plasma. How do we form our plasma? If we start with some neutral gas, in our case for plasma wake field acceleration, we use a high intensity laser to ionize gas into a plasma. And so we take this high intensity laser, which in our case is a 10 terawatt laser, and we focus it through this gas. And as it's focused, it forms this plasma filament. You notice it doesn't ionize the entire gas, it just ionizes right along this line. And that's because the plasma is made of positive and negative particles, and those will be attracted to each other and recombine after a relatively short time period, about tens of nanoseconds or so. And so in the lab, this is what that plasma filament looks like, this kind of thin, hairy pink strand you see here. This plasma, this over here is just a beam dump, so that's where our laser is being dumped afterwards. Okay, so we've talked about the plasma, now what about the wake? When I say wake, one thing you might think about is the wake of a boat. And it's very, very similar to this in plasma wake field acceleration. So if you have some sort of boat driving through the water, it can drive some sort of wake. And then in wakeboarding, actually, there can be this kind of witness that witnesses that wake and is accelerated forwards. Now this is very similar to how plasma wake field acceleration works. So in plasma wake field acceleration, we have this drive electron bunch that is moving through the plasma. And then this pink that you see here is all of the electrons in that plasma. Now, the plasma electrons, as this drive electron bunch comes through, are repelled from that electron bunch. They're repelled from the center and pushed outwards. But ions in a plasma are about 2,000 times or more heavier than electrons. So we can assume that those ions stay virtually stationary, approximately where they are. So this, we can kind of say that's an ion cavity, there's a lot of positive charge here. So if the drive electron bunch is passed, these electrons are attracted back to the center, they form this point of very high negative charge, and due to the dynamics of this wake field, a very strong focusing and accelerating field is formed here for electrons. And so if we can time a second electron bunch to enter this plasma directly behind the drive electron bunch, that electron bunch is accelerated, and we call that the witness electron bunch. Okay, so this sounds like a lot of complicated stuff. Why is this actually helpful? Why is this useful? So this is SLAC National Laboratory. This used to be a 3-kilometer long linear accelerator. Now it's divided into 3 individual pieces, the LCLS portions, and the central kilometer is facet 2, which is where plasma wake field acceleration experiments are currently done. Most of that 1 kilometer is a conventional accelerator, and in that 1 kilometer, electrons gain about 10 giga-electron volts of energy. So if we zoom into this just really quickly, you see kind of all of these orange pieces are those tubes I showed at the very beginning, those accelerating bits, electromagnetic waveguides. And in that 1 kilometer, electrons again gain 10 giga-electron volts of energy. Now if we zoom into this experimental area here, there's a lot of focusing elements and diagnostics, but what's important is kind of focus on these 2 cameras here. Between those 2 cameras is where we form a plasma for plasma wake field acceleration. And that distance is about 1 meter. In that 1 meter of plasma, the electrons gain another 10 giga-electron volts of energy. So plasma wake field acceleration is about 1,000 times more effective than conventional accelerators. Now, the effectiveness and the quality of the electron bunches coming out of plasma wake field acceleration depends largely on the plasma source's density profile. So density profile consists of both the plasma's density, of course, which we approximate in plasma wake field acceleration is often around 10 to the 16 or 17 particles per centimeter cubed. And then it also consists of the dimensions of that plasma filament. So on the length of about 50 to 100 centimeters and a width of about 100 to 200 microns. Now these measurements are based on simulations and some indirect measurements, but this width and the density have not been directly measured before. And so we want to directly measure this so that we can make sure our density profile is what we expect, and so that we can improve it if we need to for better plasma wake field acceleration in the future. All right, so we want to make a direct measurement of this transverse density profile. Well, the plasma expands very quickly. It expands on the order of 10 picoseconds. The electrons actually enter this plasma about 2 picoseconds after the plasma has been the gas has been ionized into a plasma to ensure that it gets the initial density profile. After about 10 picoseconds or more, the plasma expands very quickly and then recombines. So we need something very, very quick, very fast. Electronics, the fastest you can get an electronic measurement is usually on the order of nanoseconds, which is 2 to 3 orders of magnitude too high. So we'll use something faster, we'll use a femtosecond laser. Now, the plasma itself is very low density, 10 to the 16, 17 particles per centimeter cubed. It's quite low density. Kind of the normal atmospheric pressure is about 10 to the 19 or 10 to the 20 particles per centimeter cubed. So this is about 3 or 4 orders of magnitude less than that. And we also have a very narrow, about 100 micron wide plasma filter. So we need a high sensitivity, and the easiest way to do a high sensitivity measurement with a laser is to use interferometry. Okay, so a quick recap on what is interferometry. Most of you probably know, but we'll kind of look back at it again. Interferometry, if you take kind of a single laser beam and you split it into 2 beams, those 2 beams travel 2 separate paths and are then recombined into a single piece. Now, if those 2 paths are exactly the same, then the sum of those beams will be exactly the initial beam that went in, or twice the amplitude of a single beam. However, if one of those paths is slightly different, for example, one of those paths has to go through a plasma, for example, then you'll get a slight phase difference between those 2 waves, and you'll have a slight difference in magnitude as well between those 2 waves. And so in interferometry, quite often you're trying to measure this tiny change in amplitude there. Now, in our case, instead of using 2 different paths, we actually have our lasers travel the same exact path, but they're separated in time. And the way we do that is we take advantage of something called birefringence. So a birefringent crystal is a crystal which allows one polarization of light to pass through it faster than the perpendicular polarization of light. So if you take an initially vertically polarized pulse and you send it through a birefringent crystal, which is at 45 degrees, then that pulse will be divided into 2 pulses, which are each polarized at 45 degrees. One kind of ahead because it got to travel through this fast axis, it got to travel faster through that birefringent crystal. And then the perpendicular direction was slowed down by this birefringent crystal and forms the second pulse. Let's take a look at those, a closer look at the polarization real quickly. You start with a vertically polarized pulse, and then afterwards you have 2 45-degree pulses, and you'll notice those pulses are about half the magnitude of the initial pulse in both the vertical and horizontal directions. All right, so we use birefringence to split our initial pulse into 2 separate pulses. Now, since our plasma is ionized by a laser, we can time our laser to ionize the plasma right between the reference and the probe pulse. This means that the reference pulse passes through our chamber before there's any plasma, and then the probe pulse passes through the plasma and experiences a slight phase delay. We recombine these 2 pulses using a second birefringent crystal, which you'll notice is at 90 degrees for the first one. So it now allows the probe pulse through faster and slows down the reference pulse. If this plasma wasn't here, we'd get a perfectly vertically polarized pulse again, just like we had before. But due to the plasma being there, you can think of the probe pulse as getting a slight rotation. And so due to that, we'll have a slight horizontal polarization component now. And so we can split this into its vertical and horizontal polarization components using something called a Wollstone prism. And then we basically look at the difference between those 2 using a balanced photodiode. All right, so now this is a math slide. If you want to zone out for a slide, this is the one to do it on. So if we start with a reference pulse and a probe pulse, the reference pulse is just this E naught cosine omega t. The probe pulse has these additional 2 phase values, though. The change in phase due to the plasma, this is what we're really interested in measuring, and then this phi naught, which is also a change due to the difference in the thickness of these 2 crystals. Now, when we get to the Wollstone prism, those two are added together and subtracted together in the horizontal and vertical directions. And the balanced photodiode measures the difference between these two. It measures the intensity difference between the top and the bottom here. And so that intensity difference can be represented by E naught squared cosine of delta phi plus phi naught. Now, if we can make this phi naught, the problem is if phi naught is approximately 0, then we have cosine of delta phi. But if our change in phase due to the plasma is very small, as delta phi approaches 0, the cosine of delta phi approaches 1. And that gives us very little sensitivity because we'll just basically be measuring out the intensity of our initial pulse every single time. And so ideally we'd like to make this a sine function. And so we make this phi naught equal to n pi plus pi over 2. And by adding this pi over 2 component, we get to a sine of delta phi. And as delta phi approaches 0, the sine of delta phi approaches delta phi. So then the intensity that we measure will be the E naught squared times just the phase difference due to the plasma. And then if we can figure out a way to filter out this E naught squared, or we know our initial intensity of the pulse, then we can just find delta phi. Okay, so what is delta phi? I've talked about this change in phase, but what does that actually mean? Well, the phase equation is just 2 pi over lambda rho. The integral of a to z, which is the refractive index of the material, times that distance. Lambda probe is the wavelength of our probe laser, so that will stay constant. So then we're just dependent on the refractive index of our material, of our plasma, and then the length that we go through it. The change in phase is just a to z minus 1. The 1 we approximate the rest to be, we approximate the rest of this to be vacuum. It's a low density gas, and the reference and probe pulse are traveling through the same gas. So that shouldn't affect things too much. So we have just this a to z. Then eta in a plasma is equal to the square root of 1 minus omega p squared over omega squared. Omega p is the plasma frequency, and omega squared is just the frequency of the light that's traveling through here. The plasma frequency is only dependent on the plasma, and it's dependent on the plasma density, and the frequency is only dependent on the laser. And we can define a critical density, which is directly related to that frequency of the light. Now, if plasma density is far less than the critical density, then we can approximate this using a Taylor series to be 1 minus the plasma density over 2 times the critical density. Plugging this back into our the change in phase equation, we get this very nice all constants inside the integral, which means this is basically just multiplication times L, meaning our delta phi, our change in phase, is directly related to L times NP, or the length times the plasma density. So the most important thing we get out of this is we can make a direct measurement of our length and our plasma density. Or in this case, since we're measuring the transverse direction, our width and our plasma density. So we have a density length or density width product. All right, so we talked about the motivation. Let's go ahead and take a look. And we've talked about the physics background as well, sorry. Let's go ahead and take a look at the experimental setup. So this is a picture of our lab. And so if we kind of turn that sideways, this is a nice little diagram of our lab. You will notice we have kind of this U shape with 3 tables. Now most of this lab space is taken up by our main laser, the Centaurus laser system, which is a Ti-Sapphire laser system. We use something called chirp pulse amplification to achieve very high power. The Ti-Sapphire laser has a central wavelength of 800 nanometers. It has an energy of about 500 millijoules, and after this compressor chamber, the pulse gets compressed down to 50 femtoseconds. Now the power of a laser, the peak power of a laser, can be described by the energy over the change in time, or that pulse length. And so 500 millijoules over 50 femtoseconds gets you a 10 terawatt peak pulse. All right, so we take that 10 terawatt peak pulse, and we focus it through an Axicon lens, and that forms a plasma up here in this second experimental chamber. This is all under vacuum. All this orange is under vacuum. Okay, then we want a probe laser because we want to have a separate laser that goes transversely through this. So we take a beam sampler down here, and we take about 1% of that laser, and we send it into a probe attenuator. Now that attenuator allows us to control the energy of our pulse. Then we send it into a delay stage. A delay stage is a moving translation stage that allows us to control the timing of our probe laser compared to the main laser. We then send that pulse into a probe compressor. And this is because we missed the main compressor down here, so we need to compress this pulse from about 300 picoseconds or so down to about 100 femtoseconds. So our probe laser is about 2 millijoules and about 100 femtoseconds. That still gives us a probe laser of about 20 gigawatts. That laser is then sent transversely through the plasma and sent into our diagnostic optics over here. Okay, so we've talked about motivation and physics background. We've talked about experimental setup as well. Let's go ahead and take some look at some initial data that we've taken. So one of the first things we're interested in is how much does the plasma move? Plasma moves because the ionizing laser isn't quite perfect. It's jittering a little bit, as you can see in this video down here. That's due to the fact that there are about 100 optics, or a couple hundred optics, between the laser source and the ionization point. And so small vibrations in the table cause minute, just tiny little vibrations in the mirrors, and that can cause the laser to jitter on a shot-to-shot basis. Now, this is a distribution of the vertical position of that laser spread out around a normalized 0 point. And the vertical root mean squared jitter of the plasma is about 20 microns. Okay, so then we're also interested in the jitter of the probe laser, because ideally we'd like the probe laser to pass through the plasma as much as possible and not miss the plasma, because then we're not getting the measurement that we want. So as you can see down here, the ionizing laser is this pink in the middle, and the green describes the probe laser's vertical spread in position. The probe laser here has a far greater jitter than the plasma does. The probe laser has a root mean squared jitter of about 40 microns. And then here you can see a little video of those two pulses. Okay, so based on this, the 40 micron jitter allowed us to determine the size we want to make our probe laser. Since we know our plasma is about 100 microns thick, our probe laser was jittering about 40 microns. We decided to make our probe laser about 200 microns. That ensures that if the probe laser goes straight through the center of the plasma, great, we catch the whole plasma. If we're off by 40 microns, we still catch mostly plasma, and we're just maybe clipping at the bottom here, but we're still catching mostly plasma. Now the variation between the areas here, between them catching kind of the pulse off center here and then being centered on the plasma, is about 18% variation. And we have some methods to kind of improve that, and I'll talk about it in just a second. One of the other big things that affects our measurements is the energy jitter in our probe laser. So as you might remember, the intensity that the balanced photodiode measures is the intensity of our pulse E squared, and then the change in phase. If that delta E squared, if that energy or that intensity of the probe laser jitters and changes, then that might affect our measurements of the change in the phase. So here, based on some initial measurements of our energy, we have about a 1% energy jitter, but we have some methods with that we can improve that as well. And I'll talk about that in just a second as well. Okay, so what we're interested in measuring is kind of this 10 to the 15 to 10 to the 17. So this is a plot of the density compared to the measurable phase delay. So the phase delay is that delta phi equation that I talked about earlier, and this density is this plasma density that we're interested in. Now for this plot, I just plugged in 100 microns for the length here, and then the critical density is about 10 to the 21 particles per centimeter cubed, and the lambdas are 800 nanometer probe laser. As an example, delta phi, if we plug in all of these numbers for 10 to the 17, we get a point that's right here on this line. That's about 0.023 radians is what we would measure for that density and for that length. Okay, so based on some initial measurements and some initial work that we've done, our initial sensitivity is about 8.8 times 10 to the 16, which is a little unfortunate because we're interested in this whole 10 to the 15 to 10 to the 17 range. This is the range of densities that plasma wake-field acceleration plasma sources are usually, their density is usually in this range. And so this is very much at the top of that range, and we'd like to get much lower than that. Now, one of the initial improvements that we have to our diagnostic is a electronic signal-to-noise ratio improvement. And through that, we expect to gain about 2 orders of magnitude, so we'll be just beneath this range, which will give us enough sensitivity to be able to measure a plasma filament that's in that range. All right, so we've talked about motivation, physics, background, experimental setup, and the initial data now. Now let's take a look at the future work. So I mentioned we have a way to improve the shot-to-shot energy jitter and the shot-to-shot pointing jitter. We're going to do that by installing a probe tracking camera. This allows us to look at the probe laser, look at how it's moving around, and also track how the energy is changing from shot to shot. By tracking this, we expect to get our energy jitter down to about 0.1%, and our pointing jitter also down to about 0.1% or so. Then another future work that we have is we would like to be able to measure the uniformity of this plasma all the way along its length. And so to do that, we actually plan on installing this Axicon lens, which focuses our ionizing laser into a plasma, focuses our ionizing laser to form the plasma. We plan on setting this Axicon lens on a translation stage to move it back and forth. And by moving that Axicon lens back and forth, it basically moves our plasma back and forth and allows us to scan along that plasma. And so using this, we plan to scan the plasma to check the uniformity of the density profile, and then also to check the beginning and ends. There's some kind of density ramps that are used on these plasmas to allow for adiabatic focusing and defocusing of the electron bunches as they enter and exit the plasma. And we'd like to look at that as well. Okay, so a quick summary of what we've been working on. We developed and constructed a collinear interferometer to measure the transverse density profile of a p wave plasma source. The current largest sources of jitter are the energy jitter, about 1%, which we expect to reduce down to about 0.01% by monitoring shot-to-shot jitter. Pointing jitter, which is on the order of about 18%, but we hope to reduce down to about 0.1% by installing that camera again. And then the electronic noise, which is currently on the order of about 10%, but should be reduced to about 0.1% by installing a boxcar integrator and a lock-in amplifier, which are some electronic signal-to-noise ratio improvement devices. Some of the stuff that I've worked on personally is listed here. The full construction of the probe laser and the kind of initial data analysis of all of these kind of measurements that we've done and a lot of other stuff. So, yeah, thanks again for coming. I'm open for questions.
Questions from the audience?
Yeah, Ted?
So when you recombine the two pulses, the one that's gone through the plasma has been rotated a little bit, and so I'm imagining what passed through the birefringent crystal, will it get split up again when it passes through? Because is it at that point like not aligned with the coefficient, or does that cause a problem at all?
Sorry, say that again. When I pass through the second birefringent
The
crystal.
second, so yeah, when you pass through I guess the first time, it sounds like the kind of idea is there's a perpendicular component and a parallel component. And then when you pass through the second time, one of those has been rotated a little bit, so does it then split again?
So, yeah, the probe laser basically gains a phase delay, and that phase delay, so the polarization is still at this kind of 45-degree angle, but that phase delay means that when they're recombined, the interference between the two pulses means that there's a slight horizontal component now. Yeah, that's a good question. Romu? Sorry, which slide?
26 is this slide.
26, yes. Yeah.
Yes, so Undergraduate was fine art. Fine arts asked by your art crystals or your class.
Yeah. So fine art, we have these thick birefringent crystals. We can we have some additional birefringent crystals actually that we can rotate slightly, and so thereby increase the distance that the pulses have to travel through those. And by changing basically the virtual thickness of one birefringent crystal to the other, we can make basically the reference pulse compared to the probe pulse. We can induce kind of a phase between those two. That's on the order of pi over 2. And so by inducing that pi over 2 phase, we're able to get this from a cosine dependence to a sine dependence, if that makes sense. Yeah, good question. Amelia?
In your future first slide, when you're like trying to reduce the errors,
Yeah.
what is going to be the easiest one to reduce and why will it be hard to reduce?
So the easiest one to reduce is this kind of electronic signal to noise ratio probably. Those are some very simple techniques that already exist. Just a locking amplifier and boxcar integrator. Those are electronic techniques that basically focus in on specific frequencies. Here, so boxcar integrator, you can basically choose a box basically to integrate over where you know your signal is, and so that'll increase basically your signal compared to all of the noise. And the lock-in amplifier, you basically lock in on a specific frequency. And so since we know our signal will be coming so we have a 10 hertz laser system, so since we know we should get a signal about 10 times a second, we can lock in on that frequency and look for that. And so this will probably be the easiest thing to integrate, but the second easiest thing to integrate will probably be this camera, because we have kind of multiple methods to diagnose that camera system. Yeah, Ted?
I was going to ask, speaking of cameras, you
Yeah.
a couple times show pictures of the plasma filament.
Uh-huh.
Are you guys able to time your pictures that accurately and get the actual plasma filament, or are those references?
Sorry, say again?
Are you able to take pictures of the plasma filament when it's formed? Is that where those are from?
So, kind of. These low density plasma filaments, probably not. The plasma filament picture that I showed at the beginning of the slideshow that was done at a very high density, maybe 10 to the 19 particles per centimeter cubed or so. And that plasma was formed in argon. That was basically specifically made so we could take a nice picture of it. Normally this plasma, you'll have a hard time seeing it, yeah. If anything, you'll see kind of a faint glow of the plasma. Aiden?
Would you talk about your methods for the probe tracking camera? Because it sounds like a really cool application and you get like kind of two folds uncertainty.
Sure. Yeah, so with this camera, we can basically track we plan on setting up the full diagnostic, the measurement out of that balanced photodiode, and this camera we can basically record both of their measurements at the same time, and then compare the camera measurement to the balanced photodiode measurement. And on the camera we'll be able to see how much the laser has moved, kind of back and forth vertically, and we'll also be able to see how the energy changed from shot to shot. And so comparing that directly to the measurements of the balanced photodiode, we'll be able to basically, if the energy was lower on one shot, then we know to kind of take out a lesser energy. And so there's also a method where for the energy, we could set up a photodiode here, just a high sensitivity photodiode. And there's a full electronic version where we could basically filter out the energy that we measure with the photodiode compared to the balanced photodiode, and then just get directly our change in phase measurement compared to some like reference voltage or something like that, which makes the energy jitter even easier. But yeah, we can do that with the camera, and then with the camera the nice thing is we can also look at pointing jitter. So that 18% variance, we can basically get rid of that because we know how much of the plasma the laser went through, if that makes sense. Yeah. Patrick?
What's the motivation for taking the probe laser off of splitting it off from the main laser? And would you get any benefits from using a separate laser for the probe laser?
Yeah. So the nice thing of taking the reference laser off of the main laser is mostly timing. We can time the two of them, control the timing between the two of them, because since lasers travel at the speed of light, we just have to make sure that the basically distance from that splitting point to the interaction point, to this kind of interaction point, we just have to make sure the distance for each laser is approximately the same. This is basically exactly the same. And so, yeah, it's basically for timing reasons is the easiest. Yeah, because otherwise you're trying to time, so the difference between the reference and the probe pulse, the distance between those two is about 2 picoseconds. And so trying to time that with a separate laser would probably be very, very difficult. Yeah. Elena? That's a good point. My sensitivity measurements were based on if nobody is in the lab walking around. If someone's in the lab walking around, probably we lose about 10% sensitivity, something like that, or more. We saw, yeah, I have some awesome videos on my phone of Elena walking around the back of the lab and our balanced photodiode measurements just bouncing around wildly all over the place. So yeah, that's a good question. Probably about 10% or so. Ideally, we'd want to kind of automate this and set this up so that we can control it from outside the lab, so that there's nobody walking around inside the lab. Good question. Yeah, Roman?
What's the motivation to use a high-relay counter instead of a constant counter? Because the constant is continuously stabilized time with the humbles.
Yeah, that's a good question. The collinear interferometer basically guarantees they travel exactly the same path, and the only difference in the path length is this plasma. And so that's kind of one of the main reasons. Also, it's easier to set up instead of having to very accurately align two separate paths to make sure that your calibration is perfect. In this case, we just set up two birefringent crystals at 90 degrees to each other. And thereby we know, like, so long as we can get the timing worked out correctly, at least that way we know that, yeah, they're traveling exactly the same path, and we don't have to worry about that too much. That's a good question. Simon?
You've talked about how we like accelerate electrons and like why we're doing this to accelerate them better, I guess.
Mm-hmm.
But like, what's the end? Like, where are the electrons going? They're not just getting dumped, right? We're just like accelerating it, and then like, there you go. We accelerated an electron.
That's a good question. So accelerated electrons are very helpful for various things. One of the kind of biggest applications is X-ray free electron lasers. So making X-ray lasers, which is basically, yeah, it's very difficult to make X-ray lasers out of just basic light because your laser gets very, very inefficient. You lose a lot of power due to just spontaneous emission. So one way to make an X-ray laser is to use electrons and to wiggle very high energy electrons through a magnet, through some flipping magnets. It's called an undulator, basically. It flips magnets back and forth and wiggles those electrons and then produces X-ray lasers. And X-ray lasers are great for like biology and chemistry because they can look at proteins and cells and stuff like that. And so, yeah, that's kind of one of the biggest applications of this X-ray free electron lasers. Good question. Awesome. Any more questions?
Okay, well, thank you. We'll excuse the audience, and then the committee will stick around, so thank you for coming.